Welcome. Today, we're diving into the solid principles in Java, a set of object-oriented design guidelines that help developers create flexible, maintainable, and robust software. These principles were introduced by Robert C. Martin and have become essential for anyone looking to write clean, scalable code. Throughout this video, we'll explore each principle with practical Spring Boot examples, showing how they can transform your codebase. Whether you're a beginner or an experienced developer, understanding Solid will help you avoid common pitfalls and design issues. Let's start by understanding why Solid matters in modern software development. Solid principles are more than just theory, they're practical guidelines that every developer should know. By following Solid, you reduce the risk of bad design, making your code easier to understand, maintain, and extend. Poor dependency management can lead to rigid, fragile, and hard-to-change code. Solid helps you manage dependencies effectively, ensuring your software is both flexible and reusable. These principles are especially important during the design phase, where decisions impact the entire software lifecycle. Let's see how each principle contributes to building better software. Solid is an acronym representing 5 key design principles: single responsibility, open-closed, Liskov Substitution, interface segregation, and dependency inversion. Each principle addresses a specific aspect of software design, working together to create systems that are easier to manage and evolve. In the next scenes, we'll break down each principle, explain its core idea, and provide real-world Java examples. Let's begin with the single responsibility principle. Single responsibility principle, or SRP, states that a class should have only one reason to change. In other words, each class should focus on a single responsibility or functionality. When a class handles multiple concerns, it becomes harder to maintain and more prone to bugs. SRP encourages modularity, making your code easier to test and update. Let's look at how this principle applies in a Spring Boot application. Imagine a Spring Boot service class that manages both user operations and notification logic. This class now has 2 reasons to change: updates to user management or changes in notification handling. Such a design violates SRP, making the code harder to maintain. If either responsibility changes, you risk breaking unrelated functionality. This example highlights why it's important to separate concerns early in your design. To adhere to SRP, refactor the class into 2 separate services, one for user management and another for notifications. In Spring Boot, this means creating a user service for user operations and a notification service for sending emails. Each service now has a single responsibility, making the application more modular and easier to understand. This separation also simplifies testing and future enhancements. Now that we've seen how SRP improves modularity, let's move on to the open-closed principle. This principle ensures your code can grow and adapt without requiring major changes to existing classes. It's all about making your software open for extension but closed for modification. Let's see how this works in practice. The open-closed principle, or OCP, states that software entities like classes and modules should be open for extension but closed for modification. This means you can add new features by extending existing code, not by changing it. OCP encourages the use of interfaces and abstract classes, allowing your system to evolve without breaking existing functionality. Let's look at a Spring Boot example. Suppose you have a message service in Spring Boot that only processes text messages. If you want to add support for image messages, you'd need to modify the existing class, which violates OCP. This approach makes your code less flexible and harder to maintain as new requirements emerge. Let's see how to improve this design. Follow OCP, introduce an interface called Message Processor. Then, create separate classes for each message type, such as Text Message Processor and Image Message Processor, both implementing the interface. Now, you can add new message types by creating new classes without touching existing code. This design makes your application more extensible and robust. With OCP, your code is ready for extension. Next, let's discuss the Liskov Substitution principle, which ensures that subclasses can stand in for their parent classes without causing unexpected behavior. This principle is key to building reliable and predictable object-oriented systems. The Liskov Substitution principle, or LSP, states that objects of a superclass should be replaceable with objects of a subclass without affecting the correctness of the program. In other words, subclasses should enhance, not break, the behavior of their parent classes. Violating LSP can lead to unexpected errors and fragile code. Let's see how this principle applies in Java. Consider a user class and an admin user subclass in Spring Boot. If admin user overrides a method from user and throws an exception instead of extending the behavior, it violates LSP. This means that code expecting a user might break when given an admin user, leading to runtime errors and unpredictable behavior. To adhere to LSB, ensure that subclasses like admin user extend the behavior of their parent class, not restrict it. For example, admin user can provide additional functionality while still supporting the base class's contract. This way, you can substitute any user with an admin user without breaking your application. It's a simple change that greatly improves code reliability. Now that we've covered LSB, let's move on to the interface segregation principle. ISB helps you design interfaces that are focused and relevant, avoiding the pitfalls of large, general-purpose interfaces. This principle is crucial for creating modular and cohesive code. The interface segregation principle, or ISB, suggests that no client should be forced to depend on methods it does not use. Instead of creating one large interface, break it down into smaller, more specific ones. This approach keeps your classes focused and reduces unnecessary dependencies, making your codebase easier to maintain. Suppose you have a user operations interface in Spring Boot that includes methods for adding, updating, deleting users, and sending notifications. Not all implementing classes need every method, leading to empty or irrelevant implementations. This design violates ISB, making your code less modular and harder to maintain. To follow ISB, split the user operations interface into smaller interfaces, such as user management and user notification. Now, each service class implements only the interfaces relevant to its responsibilities. This segregation increases cohesion and makes your codebase more modular, flexible, and easier to test. With ISB, your interfaces are now focused and relevant. Next, let's explore the dependency inversion principle, which helps decouple high-level and low-level modules. This principle is vital for building flexible and testable applications. The dependency inversion principle, or DIP, states that high-level modules should not depend on low-level modules. Both should depend on abstractions. This principle decouples your system, making it easier to replace or modify components without affecting the rest of the application. In Java, this often means using interfaces and dependency injection. Imagine a user processor class in Spring Boot that directly depends on a concrete database service implementation. This tight coupling makes it difficult to change or replace the database logic. Such a design violates DIP, reducing flexibility and testability. To adhere to DIP, define a database service interface and inject its implementation into user processor using Spring Boot's auto-wired annotation. Now, user processor depends on an abstraction, not a concrete class. This design allows you to swap out implementations easily, enhancing flexibility and supporting unit testing. Spring Boot makes it easy to apply solid principles through features like dependency injection, component scanning, and modular service design. By leveraging these tools, you can build applications that are not only robust but also easy to maintain and extend. Let's recap how each principle fits into the Spring Boot ecosystem. Single responsibility principle encourages you to break down your services into focused components. In Spring Boot, this means creating separate beans for distinct functionalities, such as user management and notifications. This modular approach simplifies maintenance and testing, ensuring each service does one thing well. The open-closed principle is all about extending your application without modifying existing code. In Spring Boot, interfaces and polymorphism make it easy to add new features, like supporting new message types, by simply creating new classes. This approach keeps your codebase stable and adaptable. Liskov Substitution principle ensures that your subclasses can always stand in for their parent classes. In Spring Boot, this means designing your beans and services so that they extend functionality without breaking expectations. This leads to more reliable and predictable applications. Interface segregation principle helps you design interfaces that are just the right size. In Spring Boot, this means creating focused interfaces for each service, ensuring that classes only implement what they need. This reduces unnecessary dependencies and keeps your code clean. Dependency inversion principle is easy to implement in Spring Boot thanks to dependency injection. By depending on abstractions, your high-level modules remain decoupled from low-level details. This makes your application more flexible and easier to test or refactor. Ignoring solid principles often leads to common design issues like rigid code, high coupling, and low cohesion. These problems make your application difficult to maintain and extend. By applying solid, you can avoid these pitfalls and ensure your code remains clean and manageable. Following solid principles brings many benefits. Your code becomes easier to understand, maintain, and extend. It also improves testability and reduces the risk of bugs. These advantages are especially important in large, complex systems where change is constant. In real-world projects, solid principles help teams collaborate more effectively. With clear responsibilities and modular design, developers can work on different parts of the system without stepping on each other's toes. This leads to faster development and fewer integration issues. Solid principles often go hand in hand with design patterns. Patterns like strategy, observer, and factory are easier to implement and maintain when your code follows solid. By combining these approaches, you create systems that are both powerful and adaptable. Solid principles make your code more testable. With clear interfaces and decoupled components, you can write unit tests for each part of your application. This leads to higher code quality and confidence in your releases. When your code follows solid, refactoring becomes much simpler. You can update or replace components without worrying about breaking the rest of the system. This flexibility is crucial for keeping your application up to date with changing requirements. Solid principles support scalability by encouraging modular and extensible design. As your application grows, you can add new features or services without rewriting existing code. This approach ensures your system can handle increased complexity and user demand. Maintainability is a key benefit of solid. With clear responsibilities and decoupled components, your code is easier to update and debug. This reduces technical debt and ensures your application remains healthy over time. Solid principles foster better collaboration among developers. With well-defined interfaces and responsibilities, team members can work independently and integrate their work smoothly. This leads to more efficient development and fewer conflicts. Agile development relies on the ability to adapt quickly to change. Solid principles make your codebase more agile by supporting incremental updates and rapid feature delivery. This adaptability is essential for meeting evolving business needs. Many successful software projects use solid principles to manage complexity and ensure long-term success. By applying these guidelines, you can build systems that are not only functional but also resilient and future-proof. The Java community widely embraces solid principles, integrating them into frameworks like Spring Boot. By following these best practices, you join a global network of developers committed to writing clean, maintainable code. Mastering solid takes practice. Start by applying one principle at a time in your projects. Over time, you'll develop an intuition for clean design and recognize opportunities to refactor your code for better structure and maintainability. There are many resources available to deepen your understanding of solid, including books, online courses, and community forums. Engaging with these materials will help you stay updated on best practices and new techniques. Understanding and applying solid principles can boost your career as a Java developer. Employers value clean code and maintainable systems, and solid expertise sets you apart in interviews and on the job. In summary, solid principles are the foundation of clean, maintainable, and scalable Java applications. By applying these guidelines, you ensure your code is ready to meet the challenges of modern software development. Keep practicing, stay curious, and continue refining your skills. Thank you for joining this journey through solid principles in Java. Start applying these concepts in your next project and see the difference they make. For more advanced topics, explore design patterns and best practices in Spring Boot. Happy coding!